Good afternoon, everyone. I apologize again. I cannot be here today, but here's our schedule. So I will spend about 30 to 40 minutes introducing the last important component in this chapter, namely the principal component analysis. And during the playing of the recorded video, if you have any questions or if you feel unclear, you can just hands up and let the TA to stop playing the video and ask questions, and the TA can help you clarify the problems which you might have in the whiteboard. And of course, this video has already been uploaded to YouTube, and we will release the link after the class on cameras. So okay, let me start. So I will firstly briefly review what we have learned in previous lectures, namely singular value decomposition and eigen decomposition, and then that both decomposition will finally lead to the principal component analysis. And our introduction of principal component analysis is a little different from the traditional way to explain it, that is from the statistic component, but they are totally equivalent. So if you have taken the probability class before, you might have another interpretation, but from mathematical perspective, they are the same. So it's better for you to have multiple understanding for the same piece of knowledge. Okay, so first let us review singular value decomposition. This is the most widely used matrix decomposition. So for an arbitrary matrix A, which we assume is shaped to be n by d, that means n can be not equal to d, right? So the singular value decomposition says that A can be written as the multiplication of three matrices, right? Namely U, S, and transpose of V. And here U is n by n orthogonal matrix, and V is d by d orthogonal matrix. And here S is n by d diagonal matrix. So as we emphasized many times, right? So orthogonal matrices means that all their columns are orthogonal to each other. So if we write U in terms of their columns, so U1, U2 to UN, U is n by n matrix. That means it contains n columns. So it means that all those columns are orthogonal to each other. And similarly, if you write V in terms of their columns, V1, V2, continue to VD, those columns are also orthogonal to each other. And the columns of U are called left singular vectors, and columns of V are called right singular vectors. And then we can try to look at the layout of S, right? So as we just mentioned, S contains the singular values, right? So S is a diagonal matrix, but when n is not equal to d, what does this diagonal matrix mean, right? So if n is bigger than d, so S will look like this, and then we can pick up the top d rows to form a sub d by d submatrix, and all the singular values will stay on this line. That is the diagonal of the sub d by d matrix. So we can write it by sigma 1, sigma 2, until sigma r, and singular value is ensured to be a positive. That means if r is less than d, then the remaining parts on this diagonal is 0, right? And also r is the rank of matrix A. So this is basically the definition of singular value decomposition. And of course, if n is smaller than d, you can imagine the shape of S will be like this. Right? You just push your refrigerator and let it lie down the floor, and then you pick up the first n rows, right? So here's n, here's n, d, and you form a sub n by n matrix, and singular values will stay on the diagonal in the sub n by n matrix. So here's sigma 1, sigma 2 until sigma r. So this is singular value decomposition, and I hope everyone of you will be is familiar with the singular value decomposition, because this is extremely important. And then we introduce the eigenvectors and eigenvalues, right? Because eigenvectors and eigenvalues will form another extremely important matrix decomposition called eigendecomposition. So what is eigenvector and eigenvalue? So first, when we talk about eigenvector and eigenvalue, actually we're talking about some square matrix. So it's different from, this is very different from the singular value decomposition, which do not restrict the size of the matrix. The size of the matrix could be a rectangle, could be square, right? But for eigenvector and eigenvalue, we are only limit our range to a square matrix. So we assume our matrix is a n by n square matrix. Then if there is a pair of vector v and scalar lambda such that b times v equals to lambda times v, then we call v and lambda is a pair of eigenvector and let me erase this. A pair of eigenvector and eigenvalue for matrix B. So here V is eigenvector and lambda is eigenvalue. So remember, when we talk about eigenvalue and eigenvectors, it must be formed in pairs, because they must simultaneously satisfy this equation. So it turns out that the SVD has strong connection with eigenvector and eigenvalues. That is, we can show that for the SVD decomposition, right? We have an n by d matrix which can be written as USV transpose, right? And it turns out that the left singular vectors of A, that is the columns of U matrix, right? U1, U2 until UN, and the corresponding square of the singular values, which is sigma 1 square, sigma 2 square until sigma n square. Each pair of the left singular vector and square of the singular value forms a pair of eigenvector and eigenvalue for A transpose. So U1 sigma 1 square is a pair of eigenvector and eigenvalue for A transpose, and U2 sigma 2 square form another pair of eigenvector and eigenvalue for A transpose, and can continue until the pair of UN and sigma n square. Of course, when when the index of the singular values is bigger than R, then so if we write it like this, right? If we consider the pair of UJ and sigma J squared, right? So if J is bigger than R, then sigma J squared is simply 0 because there are only R singular values in total, right? If J is bigger than R, and then we can just use 0 to represent the corresponding singular values. So similarly, we also show that the right singular vectors, that is the columns of V, so V1, V2 to Vd, and also the square of singular values of A, sigma 1 square, sigma 2 square until sigma d square, they also form d pairs of eigenvector and eigenvalues for A transpose A. So this is a d by d matrix. That is V1 and sigma 1 square form a pair of eigenvector and eigenvalue of A transpose A, and so on. V2 and sigma 2 square form another pair of A transpose A's eigenvector and eigenvalue continue until Vd and sigma d square. And of course, here if when J is bigger than R, when J is bigger than R, of course sigma J square is taken 0 as well. So this is a very important connections between singular value decomposition and the definition of eigenvector and eigenvalues. So it is very easy to verify this result by using the definition of eigenvector and eigenvalue, and we have shown it in the last lecture. And then, given the eigenvector and eigenvalue, we introduce the eigendecomposition, right? So the to have an eigendecomposition, the square matrix must be diagonalizable, right? So if the square matrix, n by n square matrix B is diagonalizable, then we can find n linearly independent eigenvectors, which we denoted by V1, V2 to Vn, and we stack them together, we get a matrix V, and their corresponding eigenvalues, we can form a diagonal matrix. So lambda 1, lambda 2 to lambda n. So lambda 1, here is the corresponding eigenvalue for V1, lambda 2 is the corresponding eigenvalue for V2, and until lambda n, right, for Vn. We denote this diagonal matrix by L. Then B can be written as V, L, and V inverse. So this is called eigendecomposition. So this is very commonly used matrix decomposition, but people often forget about the condition that when a square matrix B can have such kind of eigendecomposition only when it is diagonalizable. So what is diagonalizable? You can check out the concept from your linear algebra course. So basically, you have a invertible matrix P such that when you do the operation that P inverse multiplying with B, then multiplies P, then it becomes a diagonal matrix. This is called diagonalizable. Of course, if B is diagonalizable, then one choice of P would be the matrix consists of eigenvectors of B, that is V, right? So this is eigendecomposition, and then we introduce a special type of matrix called symmetric real matrix. So basically, if the matrix B is symmetric and real, then we can find out n eigenvectors which are not only linearly independent but also orthogonal to each other. That means VV transpose n equals to V transpose V equals to identity matrix. Or in other words, V inverse will be a transpose of V. Then our eigendecomposition can be written as V times L times V transpose. Right? Because we simply replace V inverse by V transpose. They are the same when our n eigenvectors are orthogonal to each other. This is the definition for orthogonal matrix. And the benefit of this representation is that we can further express this eigendecomposition as a summation of the outer product for all the eigenvectors. So if you just expand this multiplication, you end up with a summation. So we have n summands where each summand is simply the eigenvalue multiplied with the outer product of the corresponding eigenvectors. Right? So in many data science and machine learning problems, actually we have to deal with symmetric real matrix. And it is common sense that use this decomposition form to replace B. And for analysis, you'll find many amazing properties and also make your derivation and make your analysis a lot more easier. So these are the important, these are another very important matrix decomposition, eigendecomposition, although eigendecomposition is not as widely applicable as the singular value decomposition, but eigendecomposition is also very useful. And then we introduce a very simple method called power iterations or power methods to compute a pair of eigenvector and eigenvalue for a square matrix B. Right? And here just briefly emphasize again, because you might need to implement power method in your homework. So let me add one more page. So basically, if you want to calculate a pair of eigenvector and eigenvalue where the eigenvalue is the largest eigenvalue, you can use the following simple iterative procedure. That is, you first randomly initialize a unit vector. So here we assume all the eigenvectors are normalized as unit vectors. So you can initialize your vector as a random unit vector. Then you can perform many iterations. Say, suppose the maximum number of iterations is set to Q. Then in Qth iteration, you simply update your vector to be the multiplication between the matrix B with the current vector. And then you renormalize it. So for, of course, to emphasize, this is actually the algorithm steps, so I can use arrow to represent the update. So that will be better. And then after the maximum number of updates are finished, you can simply return UI. So you might notice that there's a little difference between the algorithm steps I show here and the cost material. So in the cost material, in each step, actually we can ignore the renormalization step. That means we can simply repeatedly multiply our vector with b on the left-hand side, and finally, when we return the result, we do a normalization once. That's fine. So from computation perspective, this will even save more computation, but the two algorithms are totally the same. The results are totally the same. And doing this is to give you a better understanding of the procedure. And it guarantees that if your number of iterations is large enough, your return vector is an eigenvector. Eigenvector that corresponds to the largest eigenvalue of B. And why these simple iteration methods can result the eigenvector that corresponds to the largest eigenvalue, I request every one of you read the course material, because you need to use that result, that derivation, to finish one of your homework problems. So that's your homework practice, because if you can follow the derivation in the course material, it will significantly deepen your understanding of eigen decomposition. So these are the important concepts about SVD and eigendecomposition. But as we mentioned at the very beginning of our topic, we're talking about principal component analysis. But until right now, seems like we haven't started yet, right? So, and later we'll find that with these two concepts in hand, principal component analysis is very straightforward. So to introduce principal component analysis, let us go back to our previous problem. That is, we want to find some low dimensional representation of our data matrix A. So let me create a new page. So suppose we have a n by d matrix A, right? So now I want to find out an n by k matrix where k is smaller than d. That means I want to use a low dimensional matrix to approximate the original high dimensional matrix. So here, each row of A can be considered as a vector in the d-dimensional space, right? So you can consider the first row is A1, and second row is A2 transpose, until the nth row is AN transpose, right? So each A1, A2 to AN belongs to a d-dimensional space. A is n by d, right? So now, if I want to find out a low-rank representation of each A1, A2 to AN, that means in the low dimensional space, in the low dimensional matrix B, each row will be B1 transpose, B2 transpose, until Bn transpose, right? And each Bj belongs to a k-dimensional space, right? And here each Aj, right, jth row in A belongs to d-dimensional space. So I want to use this low-dimensional matrix B to approximate the high dimensional matrix A, data matrix A. And how should we do that? We previously formulated this problem to minimize SSE, right? SSE of the projection error. So basically, we want to find out a k dimensional subspace F, right? So F is determined by k orthogonal bases. So U1, U2 until UK, right? And each vector or each point in F can be represented by a linear combination of these k orthogonal bases. And then our SSE becomes the summation of the projection error. The projection error is computed by the norm of the difference between each data point in A, say AJ, and the projected vector of AJ onto F. So we denote it by pi and subscript with F, meaning the projection onto F and AJ, right? And we compute square of norm as the square of the error, and we sum over this error from 1 to n because we have n data points in this matrix A, namely n rows. So this is the objective we want to minimize to find out the best subspace F, namely the best orthogonal basis U1, U2 to UK. Right. This is our previous objective, and from the definition of the projected vector, so if I projected a vector, say x, here x belongs to a d-dimensional space, right? X could be a row in the matrix A, right? So it is simply the summation, if you still remember, right? We emphasize it several times. So it is actually the summation of the projected vector of x onto each of the bases, right? So here, because F is determined by k bases, so this projection is a summation of k projected vectors, where each projected vector is simply the inner product between the basis uj and x and times the basis uj, right? And then if we can find out the best k basis, right, that determines F. So if you here U1, U2, UK, if we can find out U1, U2 to UK, which minimizes SSE, then we can obtain the low rank or low dimensional representation X by using projection length on each basis. So we can form a low dimensional vector to represent X by using the projected length onto each basis. So we have a k projection length. So here will be a U1 x, U2 x until UKX, and this is a k dimensional, right? So similarly, if we have a A, right? So it is the first row is A1 transpose, second is A2 transpose until AN transpose, and then given our optimal U1 to U2 to UK, right? So each row of the low dimensional matrix B, say Bj, will be what? will be simply U1 B1 or U1 Bj, the inner product between U1 and Bj, and U2 Bj until UK Bj. So this is a jth row. Oh, it's not U1 Bj. Sorry, we want to calculate Bj. Sorry about this. So HBJ is jth row of B. It should be Bj transpose, right? Is simply the inner product between U1 and the original vector, which is AJ, right? And U2 AJ until UK AJ. Then we obtain the jth row of matrix B, and we can continue to finish every row of the low-dimensional matrix B. Right? And the inner product between each basis and the original vector can be considered as the coordinates. When you project AJ into this new k-dimensional coordinate system formed by U1, U2 to UK, right? And we use these k coordinates to represent. We can also use this k coordinates to represent the projected vector in the k-dimensional subspace F. That's enough. We actually do not need to use the original d-dimensional representation. So now the question becomes, how can we minimize this problem? How can we minimize this SSE? Actually, we explained it a little bit in our previous lectures, right? So basically, we can assume, in addition to U1 to UK, right, we can add extra d minus k orthogonal basis. We can denote it by UK plus 1 to UD. If we merge these two sets of orthogonal bases together, and also we assume they are orthogonal to each other, I mean the d bases are orthogonal to each other, we actually can recover the whole d-dimensional space, right? Then we can show that the norm between the difference of the norm of the difference between x and the projected vector x onto F and take square is simply the norm of what? Is simply the norm of a projected vector on the subspace determined by this d minus k orthogonal basis. So which is simply the summation from k plus 1 to d, and the inner product between each uj and x and times UG, and you add those projected vector onto UK plus 1 to UD together, and you calculate the square norm of this added vector. You get this result. And if let me add one more. If you rewrite SSE in terms of this representation, you will end up finally with a summation from k plus 1 to d, where each segment will be uj transpose AA transpose. Sorry, it's not A transpose. It's A transpose A UG. And this is your SSE. So let me give a clear writing. And if you're trying to minimize this problem seems much easier to be minimized, and add the constraint. Remember, UJ plus UK plus 1 until UD are all orthogonal vectors, meaning that their norm is simply 1, unit vectors, and also UJ, UT, their inner product is simply 0 when j is not equal to t, and here j must starting from k plus 1. Right? And if you add Laplace, if you add Lagrange multipliers into this minimization problem, which is pretty standard, right? And you can solve that actually. UK plus 1 and until UD are all eigenvectors. Are all eigenvectors of the matrix A transpose A. And then minimize SSE. You can derive this. This is pretty straightforward if you just apply the Lagrange multipliers here to solve UJ. And also you can derive that our optimal basis, which determines F, right? U1, U2 to UK are K eigenvectors that corresponds to the K largest eigenvalues of A transpose A. This is the result. This is the result. That is, if you want to minimize this SSE to minimize the projection error such that you can find out a low dimensional matrix that best represent or best approximate the original high dimensional matrix A. Those spaces are actually the K eigenvectors that corresponding to K largest eigenvalues of A transpose A. That is the transpose of the original matrix multiplying the original matrix as a result. And then when you compute the eigenvectors of A transpose A that correspond to the K largest eigenvalues, you can project each data point in A, that is each row in A, onto these K eigenvectors to get B, right? To get each row of B as B1, B2 until Bn. So now let us try to connect this result to our previous concept. So how can we compute the eigenvalues and eigenvectors of A transpose A? Remember what we can do before, right? Remember the connection between the single value decomposition and the eigen decomposition, right? So given the single value decomposition of our data matrix A, we can immediately obtain the singular vectors, the eigenvectors and eigenvalues of A transpose A by using the right singular vectors and square of the singular values, right? So to find out the eigenvectors which correspond to the largest eigenvalues of A transpose A, what should we do? We can simply perform the singular value decomposition SVD onto the data matrix A, right? And then we pick up the left K. We pick up the left K singular or right singular vectors in V as the left K columns of the right singular matrix V, right? So left K columns in V. Then we obtain the basis. And then we can obtain a low-dimensional approximation matrix B. Right? So this is results. So let me write down the result. To minimize SSE, we can simply do SVD on A, then use left K columns of right singular vectors, singular matrix V. So here A equals to U as V transpose, and if we write V as a set of columns, right? So it has D columns. We just choose the first K columns as our best basis. Then use V1, V2 to Vk. We can obtain the low rank low dimensional representation B, right? And that's simple. We can simply project each row of A onto these K eigenvectors and use the projection lens to form the corresponding key values in the k-dimensional vector, right? So, but this is not the most general case. Right? The most general case is what? So remember, up to now, when we introduce the subspace F, we introduce the subspace F here, right? We assume any point or any vector, any d-dimensional vector in F can be represented by a linear combination of the k bases, right? So any point that belongs to the k-dimensional space F, we know that P can be represented as a linear combination of the k bases, right? So here, to emphasize this vector again, so let me add an arrow on top of those vectors, right? Remember, all the coefficients can be chosen to be 0. So when we choose alpha 1 equals to alpha 2 until alpha k to be 0, that means P is 0. That means 0 will always belong to the subspace F, right? But in the most general case, actual L space can deviate from 0. So imagine, let us use a three-dimensional space as an example, right? So here's F3, right? You can, of course, choose a two-dimensional subspace F, right? Two-dimensional subspace F. I suppose I choose axis and y-axis as the basis. Then this is a two-dimensional subspace, which actually are the xy plane, right? But in a more general case, the subspace should be just a subset of the whole three-dimensional space, right? So what if I want to represent a subspace that does not contain zero? For example, I just move a xy plane upward to some distance, right? So in this new subspace, it does not contain zero. Then the question would become, if we also consider this kind of subspace, how can we minimize the SSE projection error? That is here. I minus projection F on AI and the square of the square norm of the difference, right? How can we do that? That means we actually extend the range of subspace. So previously, all the subspace we talk about, they must include the origin zero, right? But now, if we can relax this constraint, that we allow the subspace that you project your data point onto can exclude zero. Then how can we minimize SSE? Okay. So in this case, we should be aware that in this case, we'll allow the subspace to exclude zero, to exclude the origin, to parameterize the subspace. You not only need k orthogonal basis, you also need a center point C. And then for arbitrary point x that belongs to the original d-dimensional space, the projected vector of x onto F is represented as a centering point or center vector plus the summation of the projected vector. But the projected vector is now computed as the inner product between each basis and the difference between your original vector and centering vector, and then multiplying the basis. So here, let me put arrow here to emphasize it is vector. This is definition. So to illustrate this point, you actually can imagine, right? You actually can imagine that. So in a three-dimensional space, here's just one example, right? So three-dimensional space. Suppose now my subspace is here. You move the xy plane upward to some distance, right? So now, if you still want to project a vector x onto this plane, right? It is different from projecting x onto xy plane directly, right? So this will be the projected vector, because this is if you draw a perpendicular line across this subspace, right? You get a cross point, and here's your projected vector. So to obtain this projected vector, how can you do that? According to the vector addition, you actually need to first subtract x with the centering vector. So what is centering vector? It's just a align with a z-axis, right? You subtract x with the centering vector c here. You end up with this vector. And then you projected this vector to the bases. The bases are still x and y bases. You get this vector, and then you add the center vector and this vector, you get your projected vector here. So let me emphasize here. So this is our final projected vector onto F, but to get F, you need to first subtract x with the centering vector c, which is aligned with z-axis, right? And then you projected this subtracted vector here. You calculate the projected vector of this vector difference, that is between x and c, onto the first basis, which is x-axis, second basis, which is y-axis. You add them together, you get up this intermediate vector. And then you add the centering vector with this intermediate vector, which is here, right? This is center vector. You end up with the final projected vector. That's the definition of the projected vector onto a subspace which deviates from the origin. And now you can use this definition to form SSE again, right? You just substitute the projection vector, use for this. You just replace the projected vector with this definition, and you get a new objective, right? You get a new objective. You not only need to determine the best basis U1, U2 to UK, you also need to determine the best centering vector to find out the optimal subspace. And the minimization of this SSE is kind of is a little non-trivial. And so here we only give you the results. And this result are the general principled component analysis. So if you solve this SSE, you get the general principle component analysis. So basically, it's very similar to our previous case that you just restricted subspace F to include origin. You first centering the data matrix A. So let me add one new page. So we need to do some pre-processing on the n by d data matrix A. The step 1 is centering. So what is centering? You just compute the average of the rows of A. So as we mentioned that A can be written as A1 transpose, A2 transpose to AN transpose, right? So which represent its n rows, right? And then we just compute the average of these n rows. Let us denote by T, which is just the n 1 over n times the summation of each row, right? And then you just subtract each row by this average row vector. So you get A bar to be A1 transpose minus T transpose, A2 transpose minus T transpose, until AN minus AN transpose minus T transpose. This is called centered data matrix A. and second, the remaining things are the same. So the best k-bases U1, U2 to UK that determine the k-dimensional subspace F are the left k right singular vectors of A bar of the centering matrix. So basically, if you take SVD over the centering matrix A bar, so you end up with U bar, S bar, and V bar, right? So you just pick up the first k columns of V bar. So we can denote it by V1 bar, V2 bar, until Vk bar. And they are the optimal k bases. And what is the centering vector? What's the optimal centering vector? The optimal, here's optimal. The optimal centering vector for F is simply T. That is C here, is simply T. So basically, to do the principal component analysis, you just need to do two steps. The first step is to centering matrix. That is, we calculate the average of the row vectors of our data matrix. And then we subtract each row of the data matrix A by the average row vector. You got the center matrix. And second, you perform a singular value decomposition on this center matrix. You get the right singular vector set V bar, and then you pick up the first k columns, first k right singular vectors to obtain the optimal k basis. And in the meantime, I can tell you the optimal centering vector for the subspace F is the average row vector of A. That's called PCA. And if you want to compute each row of B, you can simply project each row of A bar, the centering matrix, onto this k basis. That's called a principal component analysis. So that's pretty much I want to deliver to you today. And in the remaining time, you can ask any questions. So because I don't have a chance to interact with you guys if you have any questions. So if you have any questions, you can ask TAs, and they can help you to answer those problems. And also, the remaining 10 minutes will be left with our TA Claire to introduce another applications of principal component analysis called and scaling multidimensional data, and you can just give a rough sense. Okay, and thanks for your patience, and see you on next Monday.